Thanks everyone for staying here. Appreciate your time and patience. So today I'm going to talk about the reliability-based design optimization that is implemented on the rooftop PV panel system. So I'm from Train Technologies as a modeling and software engineer. Before this position, I was doing my graduate school in the University of Illinois at Urbana-Champaign. So before jumping into this topic, I'd like to give you a bit of background introduction of the motivation in this topic. So when I was working back in school, I was working on the geothermal heat pump system, basically using the ground source heat pump, like to replace the cooling tower, using the ground buried heat exchanger. So when it comes to ground source heat pump system, there's a lot of unpredictable factors, such as the layered ground thermal conductivities, the groundwater flow, and like the length of the borehole. It really depends on the geology and other factors. So that was the very first motivation for us to implement a reliability-based method to kind of optimize both the performance and the safety of the system. So a few years later, when we working with our colleagues who are working on the solar systems, we were saying that why don't we implement this method to a PV system, since this is also a system that's based on multiple factors, which are also a lot of uncertainties and unpredictable. So if you look at the number of publications over the last 2 decades, from originally only a few hundreds of publications in the field of building PV systems to over 2,000 number of publications. This has been a heated topic over 2 decades, right? So if you look at the particular PV panel, a lot of factors can affect the performance of the system. For example, the orientation, the azimuth angle, or the installation angle, or some random variable from the environment, like the intensity of solar radiation, the solar radiation profile over the year, and some dust cover or the module degradation due to the temperature increase at the back panel. So in this case, we are kind of focusing on, one of the focuses is like the back panel temperature increase, which will decrease your performance, like the efficiency of power conversion. So to have a general big picture of how those factors affect the PV power output, we conducted a few parameter analysis, including the installation angle ranging from 0 to 60 degrees, the azimuth angle and dust cover. So the variation can be over 60% in some cases, just for information. And when you change the azimuth angle from like at different directions from 0 to 270, the difference is also enormous. And also the dust cover and solar radiation. So this is a workflow, like the general picture of how we model this RBDO method. At the beginning, from the building model, energy modeling, to have the electricity profile from the building. And we did a solar output model to predict the solar power output based on the parameter inputs, and that is the generation profile. So the RBDO algorithm is to combine the uncertainties with each of the design variables and random variables. So we're using, in this case, we're using normal standard deviation, the normal standard distribution for those uncertainties. And this workflow kind of show you how the loops work based on the initial guess for the design and random variables and cost analysis. It's not real cost analysis, but it's about minimizing the installation area. And the constraints are established at the beginning, which I will introduce that a little bit later. So there are some thresholds on some parameters that you need to satisfy those constraints to optimize. And then the PMA method in the reliability analysis. And at the end of the day, you'll have optimal design for design variables. So the building energy modeling is conducted in Trace3D Plus, which is a software developed by Train Technologies. And this is a high-rise apartment, which has 20 floors in total. Each of the floor contains 4 units of 1-bedroom units. And this is a typical American apartment that is located in, we're simulating it in both Minneapolis, the United States, and Hangzhou, China. So the climate zone on the floor plan has been shown on this slide, and the breakdown of the energy consumption, including heating, cooling, pumps, fans, and so on. So this is an example in Minneapolis, which is a heating-dominated climate, as you can find from the figure. And we have a test bed experimental study in China, which is located in Hangzhou on a 3-story building. We have the temperature sensors. So as I mentioned earlier, one of the focuses is the back panel temperature and how that affects the performance of PV. So on each of the PV module, there's a RTD installed at the back panel to monitor the surface temperature and also the air temperature. And also the heat flux sensors were also installed to monitor the heat flux magnitudes at the inner side and outer side of the roof. So we also compared the simulated outputs from MATLAB with the experimental output from the PV panel recorded by the instruments. And in general, they are matching each other, except for some of the cases when the batteries are charged fully and there's a discrepancy between the 2 sets of results. But in general, the computational model in our code works well. And the instruments, the test parameters, and the range and accuracy of these instruments are listed in this table and also in our paper. So this is the kind of a more detailed RBDO algorithm. I didn't put all the equations here, but this is to give you a general idea of how it works. It starts from the objective function, which in this case is the minimization of installation area. PR represents the probability, and G is the performance function or the objective function. So when G smaller or equal to 0, that means your optimization is successful. The reliability is higher than the requirement. So beta T is the target reliability. So the objective function is like the probability of your performance function is successful is bigger than the required probability of reliability. And the capital D and X represent the design and random variables. The random variables mainly refers to those variables that you cannot control by the designers, like the weather, solar radiation, like the dust cover, or like the profile of temperature, ambient temperature. So the lowercase d is the mean value for each of the design variables. And after that, there's a linearization for the space from the initial variable space into a standardized normal distribution space. And then the performance measurement approach is to trying to use the gradients of beta regarding each design variable. This is like a sensitivity analysis to search for the next searching direction, to give you the best direction to search for the next step. And to compute the partial derivatives in U space, we are typically using finite difference method that is used for calculating numerical partials. And in this case, there are 5 variables in total. This is a more straightforward diagram to show you how it looks like when it's on the figure. So typically in a deterministic optimization, when there's no uncertainty, no probability considered in the optimization, the red dot is exact the value that your final result is. But when you consider the uncertainties for each of the parameters, the results may vary, might be different from all perspectives. So the LSF is the limit state function, which is the surface of the failure. When your performance function, so this separates the safe region and failure region, right? So when you want to have most of your potential outputs fall within the safe region, well, you also allow like a tolerance of failure, which like maybe less than 10% in some cases. So this is to calculate the reliability index beta. This is actually the distance from the original point, because you have linearized your original variable space into a standardized space, right? So this is a standard circle, and the reliability index beta is the distance from the original point to the closest point at the failure surface. And correspondingly, the probability of failure is 1 minus reliability. And this is also mentioned in the earlier diagram when you have calculated all the partials for the design and random variables, and you can have the updated searching point based on the steepest accent directions. This is some preliminary results from when there's no uncertainty, when there's no probability, to give you a general idea of how these variables change along the variation of installation angle. For example, the SURM is the self-use rate, which is calculated by the output power from PV that is used by the building directly by the total power generation and the overall generation rate and the installation area. So for example, the SUR is decreasing, but the temperature, when you have a traditionally optimized installation angle like 25 degrees, the temperature at the back panel is higher, which also limits your optimization. And this two figures represents the case in Hangzhou and Minneapolis respectively. And similarly, when it comes to the self-use rate, if you look at self-use rate specifically, and along the effective hours simulated, when you change the installation angle from, in general, 0 to 90, and here represents some typical representative angles, there are also some differences between each of the cases. So in general, when installation angle increases, the self-use rate increases, but this trend may not align with the total power generation rate, which is why we need to compromise between different objectives. And here are the results from the real reliability-based design optimization. Firstly, for the city in China, when coupled with 60%, 70, and 80% reliability. In different scenarios, there are 5 variables in total, 2 design and 3 random, coefficients of solar radiance, temperature, and the power conversion efficiency. So their initial guesses are given at first, and you're giving also the mean values of them and the lower and upper bounds, so you cannot optimize them beyond some reasonable range. The standard deviation for beta is 2 degrees in this case, and we're comparing 3 scenarios: the baseline, the uncertainty, the low uncertainty case, and high uncertainty case. Well, in this case, case A represents the deterministic case when there's no reliability concern. And as one can observe, when you're looking at the low uncertainty, the high uncertainty case, when the reliability level is 60%, you will have a significantly higher installation angle to avoid excessive temperature at the back panel. And when you have a 80% high uncertainty case, the installation angle reaches beyond 61 degrees, and so as the installation area. And also one of the important conclusions is that we can successfully converge all the results when combining the RBDO with the solar model, which is quite important because you want to have all your constraints satisfied. So from this figure, you can observe that all the residues converge to equal to or below 0 because that's the safe region. So for example, constraint 1 and constraint 2, initially, based on the initial values that are calculated around negative 0.12 and negative 0.16, and they are slightly increasing because you're not only satisfying the safety constraint, you're also trying to optimize the system to minimize the cost and installation area, right? For constraint 3, which is the temperature constraint, initially it is above 0, which means this was not satisfied in the first place, and then it converged close to 0 but negative, which is what we want. So the self-use ratio, which is 61.2%, and the increase of panel temperature is controlled exactly at a threshold, in this case 90 degrees Celsius. And the temperature increase may be easily elevated beyond such tolerance and potentially lead to component degradation when conducting a deterministic optimization. And so if you look into if you compare the local results and the kind of global results, the global results refers to the reliability level varying from 60 to 85%, and the local is like 80 to 85%. They are similar and they are following the similar trend. When you're increasing the reliability level, typically the model, the algorithm will recommend that you should use higher installation angle to make it safer. And this is the result from Minneapolis. So since they have different trains for those parameters, we have implemented different constraints. In this case, we want to have overall generation ratio above 1.3. Self-use rate should be bigger than 0.6, and maximum temperature increase should be below 35 degrees Celsius. And here are the results. The table shows you when the reliability level is the baseline case or the low uncertainty or the high uncertainty, and how the standard deviations change. And as you can see, in low uncertainty cases, the standard deviations are pretty low, like 0.2 for the azimuth angle and 0.02 for the coefficients profile. And in high uncertainty cases, they are pretty high. And if you note, at the bottom of the table, there's a red highlighted row which is unconverged because of the high uncertainty and the 85% reliability level. So in some cases, if you turn up the reliability level too high, and when you have highly uncertain variables together, that will give you the divergence in the algorithm. So this is one of the things we want to check every time we run the optimization algorithm. I didn't put a conclusion slide because I think I covered basically everything here. So we have successfully run the combination of RBDO and solar model. We also have confirmed that when you have reliability concerned in the model, it will significantly affect the optimal design variables. So if you have any questions, I'll be glad to answer. Thank you very much.
Thank you. And we have a little bit of time for questions. What kind of the launch that's the first question. You have a question. I'm trying to understand what the reliability is really captured. Explain that.
What is the reliability capture?
Yeah, in terms of like, I don't know, I think of reliability in a very general sense, and I didn't catch.
It's like the probability of the system constraints are not satisfied. So you have three, no, like one minus that would be the reliability.
Yeah. So you brought up this figure. Can I, is it something like, oh, do you have a reliability index?
Yeah, it's
like
basically a
distance of that. I see. And then can I also see from this diagram, or can you explain why reliability and uncertainty are conflicting with each other? You said that they kind of compete, and that's why you're going to converge.
Well, yeah. So in some cases, if you have high uncertainty in parameters, which means your calculated results may vary very differently. Like will be a very large range of outputs. So that will make it harder to make sure the probability of failure is low enough. That's why it makes it hard to converge.
Can I see in this picture, like, is there a bigger, like, wall around the origin or something?
Like when there's uncertainty is high.
The conflict between reliability and uncertainty, I'd love to, if I could visualize it.
We don't have a specific visualized picture at this moment, but
Okay,
we can.
I like this one a lot, so I want to make it do more work.
Yeah.
You have a question? Please.
Thanks a lot for the presentation. I was just wondering about your assumption on the assumption of normal distribution. How do you think the results will change with a different distribution?
That's a good point. So this is kind of a preliminary study at this moment. We're trying to use a very standard normal distribution based on my previous experience on ground source heat pump system. So typically we're looking into some literature review and trying to collect those data from different locations and see how it varies. Like if it follows the standard deviation, or there should be a correction factor that applied to the distribution, or we're using different distribution patterns. But at this moment, we're using normal distribution for simplicity.
The rationale for normal distribution was because in the previous study you had used normal, so you just continued with the same methodology.
That's one of the reasons.
All right, any more questions? Okay, thank you very much to all our speakers and for the questions.